Good afternoon to all the participants of this particular course that we are running on the advanced geoinformatics tools for disaster risk reduction. And today's lecture, I'll be talking on the part from the perspective of flood hazard management, how this technology is helping. So I'll be, I'm working as, my name is CM Bhatt and I'm working as scientist in Disaster Management Sciences Department of Indian Institute of Remote Sensing, Dehradun. So today's talk the objective of this session will be to help in familiarizing about geoinformation technology potential and applications for flood hazards through some case studies that we have done and through also that have been done by other researchers. Will take you, and at the end of this session probably you will be much more knowing about this tool or technology in the field of flood hazard. Since you may be from different fields, so I'll try to also give some basics how this particular technology helps for flood with some other examples. So let us start the talk. The first thing that comes to mind once we see the disasters statistics across the globe or in recent time, this is one of the picture that on the right side you are seeing that has come up, which shows 10 disasters that have struck in 2021, and they have caused a huge economic losses as well as the loss in the form of human lives and property damages. But what more striking is that these all disasters have an origin that is related to climate-driven extreme weather events. If you see among this circle, out of those 10 disasters, you will find more of them are like hurricane, floods, storm, floods, cyclone. All these have a hydrometeorological, some kind of origin, more of hydrological in nature. And also, if you see the circle, India has a position where in 2021 we had cyclone Yas, and after some time we had cyclone Taukte, which affected the eastern and the western part of the country. And if you see the statistics, it says flood affects almost 50% of the flooding affected the highest number of people, accounting for 50% of the total affected, followed by storms, which accounted for 28%. So 50% of the people were affected by the floods. So floods are, are a cause. Floods are cause of economic damages, and as well as the loss of lives, and also the loss of more people getting impacted by these kind of disasters. Now, knowing that floods are one of the most prominent among the disasters, what is a flood? Let us see. A flood is a relatively high flow which overtakes natural channel provided for runoff. That means, if the carrying capacity of the channel is, overtaken, or it exceeds that capacity, the water overflows this bank and inundates those areas that are generally not flooded. So this is the definition, and we have different types of floods, which we call as riverine floods, flash floods, coastal floods, urban floods. Some of the floods we are very much familiar, like riverine floods. From long back, riverine floods are known to all of us. That in monsoons, rivers get flooded. There are floods suddenly, of sudden nature due to dam burst or sudden cloud bursts, like flash floods we have, and the floods that are affecting the coastal areas due to cyclone or tsunami, induced kind of surge. Those are coastal floods, and urban floods now are more in news because of the flooding in the urbanized area, and that is because of the unplanned or concretization of the surface in the urban areas, which has modified the hydrograph. You are seeing on the right side, on the lower side, or right side, the hydrograph. There are two hydrographs. So one is before the urbanization, which has a lower peak and is relatively flat, whereas the other hydrograph, you are seeing there is sudden peak, because there is no infiltration of the water, and whatever water falls on the surface of the earth, it turns to be a runoff and causes most of the damage especially in the urban areas. Now, there are a number of causes which are inherent either to the area because of its physical characteristics, and the problem gets aggravated by the anthropogenic factors, which basically are human induced because of the human activity or the modification of the land. So physical factors may be morphometric, geological, terrain, climatic. They are specific to that area, and we do not have much control because they are inherent to the nature. But these parameters get further aggravated once there is a modification in the land cover or deforestation, and if our river management activities are not proper by the concrete, the dams, embankments, urbanization, all these activity enhance the problem. And because most of the population is moving to urban areas, so there is more people coming to the urban areas, and therefore we have more problem of flooding in the urban areas in recently in news. And if you see 68% of the world population projected to live in urban areas by 2050, around 68% will be moving to the urban areas by 2050. It has been projected, and 90% of this increase will be taken in the African and the Asian continents. So that is why the pressure is increasing in the urban areas, and we have such kind of problem. Then coming, if we see, especially if we focus on the Indian side, every year these floods are, each flood is unique in nature. Every year we are seeing a flood which is much different than the earlier flood that we have faced. And the intensity, the magnitude, and the severity, or all in all dimensions, it is unique, and it looks as if this is the most hazardous among all. If you recall, in 2021 we had Chamoli flash floods in Uttarakhand. 2020 we had Hyderabad floods in late October. 2019 we had Bihar. 2018 we had Kerala. 2015 we had Chennai floods. So each flood is unique in nature by its origin, by its characteristics. So but what happens, since these floods are having a regional, these are regional phenomena, and they are temporal. Flood lasts for a longer period. It is not one day event, or flood does not happen on a flood one day and it goes away. Once the flood initiates, the river starts swelling up. It continues to be there for a week, 10 days, and even may continue for months. Like we have floods along the Brahmaputra or the river Ganga in Brahmaputra. We know once the monsoon starts, these areas are chronically prone to floods and have flooding problem for a larger duration and a larger spatial extent. So from the perspective of flood, two things are more important. The extent is large, and also the duration. It is not a one-day phenomenon, so it continues for day and day. So we require, in such cases, the information that is required is more of the spatial extent. How persistent the water is lying in those areas. What could be the soil moisture, precipitation, river morphology. We need to assess the risk. We need to mitigate the problem. So in times of flood hazards, these information is very much critical. And generally what happens, because of the limited time, limited resources, financial constraint, we do not have much information on this particular phenomenon. And if we go by conventional means, like we were doing earlier, by sending our people or team to assess the situation, whether in times of flood or before the floods, it will take larger time because the floods are have a regional, they affect larger areas, and their flooding continues for months. So it is not feasible, to do the assessment or whatever flood mitigation or strategy we are trying to develop conventionally by sending our team onto the ground. So therefore, what has happened in recent years, number of geospatial technologies have evolved, which have aided particularly the flood hazard or the flood risk management has been benefited from the emergence of these technologies. Today, if you see, we all are aware, remote sensing, GIS, GPS, web GIS, mobile apps, communication networks, IT, database management systems, all these are now a part of our flood emergency management framework. And today, if we see, from remote sensing, we have different platforms, like we have drone, we have UAVs, at high resolution satellite images. And GIS also, we are seeing a lot of advancement. GPS, we have location based services, mobile web GIS, you can now access the flood information on the portals, through portals. Mobile apps are being more popular. There are different kind of apps which are being used to get information, collect data. So the entire cycle of flood hazard management, whether it is from the starting of the disaster, pre-flood, during flood, post-flood, gets benefited. And these, it is not one single technology that is helping the flood hazard management. It is a convergence of geospatial technologies, because today GPS is also being used, GIS, mobiles, satellite images, everything is being, drones are being used to get information. And also the computing technologies that are emerging are being used, and all they converge and help towards better flood disaster risk reduction. Since it is geospatial, we all know geospatial data is the data which has the information about its location. That we know what are the coordinates where on the earth it lies, and what is the attribute. So geospatial data is characterized by the attribute information, that is what is the data about and where is that data located on the earth. So that is what we mean by geospatial, and there are a number of sources that help us to collect the geospatial information, either through remote sensing, GPS, or ground surveys or photogrammetry. So there are a number of or maps that help us to collect this information. And once this information is there, geographical information system, this, you must be aware about this kind of softwares which help us to keep the record, update the data, query the data, do the measurement, analysis, retrieving of data, visualization of the data. So there are sources which allow us to capture the data. There are sources, there are tools which allow us to maintain and update this data, and also do analytics on that data. So one of the most important tool in this entire cycle is the remote sensing data. And why it is very important, remote sensing is, collecting of data, without being in physical contact of the object. And there are different kind of platforms, we have seen. And why it is so important, it is because of it has a global coverage. It gives you a synoptic coverage. It can cover those areas which we cannot cover during the times of flooding. We cannot be on the ground. It allows us to have a pre and post comparison. That means these satellites are orbiting the Earth, so they take the picture when there was no flood, and they also give you the picture when there was flood. So they allow you to help in temporal monitoring. That means you can have today, tomorrow, and day after tomorrow, you can have a picture how the flood is progressing or the receding. It allows you to map the earth in all weather conditions. That means you can map the floods, whether there are clouds or whether there are no clouds. That means in unfavorable conditions also, you can map the extent of flooding and these satellites being at a higher, at a higher altitude, so they are not prone to damages. They are at 600 or 700 kilometers, so they are not prone to damage, unlike our ground instruments, like we have river gauge on the river, which get impacted during the floods. Now, remote sensing images, from this remotes, whatever these satellites are launched, they capture, they take a picture of the earth, and once we get the picture of the earth, we are able to map the floods. And once we get that flood hazard information, that information is important not only to know the spatial extent, but also that can be used in our hydrological models to calibrate or validate, or in our data assimilation techniques. So it can help you both in validation also as well as in mapping. That's why these satellite remote sensing data sets are very important. Now, earlier I was telling that we can do the mapping in either in all weather conditions. What is meant by is that we have two types of imaging. One is optical imaging, which uses the optical wavelength. Other is the microwave imaging, which uses the microwave, those wavelengths. So these optical imaging is, gets hindered because of the presence of the clouds, and these shorter wavelengths, which in the visible spectrum cannot penetrate the clouds, and therefore we are not able to see what is there on the ground. And this is the left side is one picture which shows there are presence of clouds, and below there are floods, but this beam gets obstructed and we are not able to get the picture on the ground, but we are only seeing the clouds. Whereas on the right you have the microwave imaging, which can penetrate the clouds and give you a picture of the surface, what is there on the ground, even when the clouds are present, because they are of a longer wavelength. And this is called active remote sensing. This is called passive remote sensing. One depends on the source of the sunlight. Whenever there is sun, it will work, and whenever the sun is not there, it will not give you the picture. Whereas active has its own source of light. It can work day and night. So therefore, that is why from the microwave we have data acquisition in the morning time also, and in the afternoon, in the evening time also. And whereas from optical data, you have only one imaging, during the time when it is the sun is over there. So once you get data, now you have the satellites either in optical or the microwave domain. So we also need to extract the information about the flood or the water. So let us see first the optical imaging. From the optical imaging perspective, this is on the picture you are seeing the spectral reflectance curve. So the reflectance of the water is gets impacted by the nature of the water, by the depth of the water, and the presence of the materials that are within the water. If it is a clear water, it gets completely, the water. If you see the spectral reflectance curve, in the NIR range, the wavelength gets completely absorbed, and you have a darker appearance or darker tone in the NIR band from the perspective of water. Whereas if you see in contrast, if you see the vegetation, it has a higher reflectance. So they have a contrasting nature. In NIR, this vegetation gets more reflected, and this gets absorbed, and that is where we are able to distinguish land and water in the NIR band. And if there is turbidity, if there is presence of sediments in the water, there is higher reflectance increases, especially in the red band. And and this turbid water has some sediment suspension, which increases the reflectance in the red end of the spectrum and accounting for its brownish appearance. Similarly, if you have increase in the chlorophyll or content or other substances in the water, its reflectance curve will change from the normal. Also, if the water bodies are shallow and deep, and the water is clear, they have a different kind of reflectance. You may see the water in the false color composite as dark blue, and whereas if it is turbid, you may have a brownish kind of color, which we can differentiate. So this is one of the satellite pictures from Sentinel-2A data. There are two bands, green and the SWIR band 2 and the band SWIR. So this is in the visible domain, whereas as I was telling, in the near infrared and further the water gets absorbed. Therefore, that's why it appears darker. And in the green, it is reflected more, so that's why it is not appearing darker, but little brighter. No, so that's why NIR and further are taken into consideration while we are delineating the water or trying to classify the water. This is one of the false color composite images which shows you the presence of water. And depending upon the type of water, as earlier I said, if it is deep and calm, it will have a different kind of tone. If it is recently flooded, it will have a different kind of tone. And if the water is receding, it will have a different kind of tone. And if the water is intermediate, it will have a different kind of tone. So depending upon the the type of the sediments present on the water and its depth and its turbidity, you can differentiate. Like here, this is the flood which is receding. This is a fresh flood. This is somewhere intermediate, and this is the where the water is very calm, and deep. So once you are able to identify the water in different bands, there are different techniques to classify or map the data. Either you do it visually, or you do it digitally by using there are different indices like NDWI, normalized difference water index is there, which takes a ratio between the green and the NIR, where water has a higher reflectance in green. In NIR it is very less, so it takes a ratio between the highest and the lowest and finds out you will have all the water bodies as positive values. So this indices is used to map the flooded areas. So that was from the optical data perspective. But generally during monsoons, we have a lot of clouds, and therefore this optical imaging is limited, has limited application, especially during the monsoon season, and we have to depend highly on the microwave imaging. And microwaves, it is an active kind of remote sensing, so it can measure, this radar can measure amplitude, the strength of the reflected echo, and phase, position or point in time on a waveform cycle. So radar transmits a pulse. This pulse interacts with the ground, and it is scattered in different directions. Some of it goes back to sensor, some of it goes away from the sensor, depending upon the surface nature. So radar can only measure a part of the echo which is reflected back towards antenna. Radar pulses travel at the speed of light, and the strength of reflected echo, whatever the strength of reflected echo, goes back to the antenna, it is called backscattering coefficient, or the sigma naught, and it is expressed in decibels. Though this is a little different from the optical imaging. Optical, we have different kind of bands, and we have a reflectance curve. But here the interpretation and how we look at microwave is little different. So radar, in microwave, the radar observation parameters depend upon the frequency or the wavelength, polarization, incidence angle, and all these are the parameters which are inherent to the mission or the satellite or the which is planned, and also to the ground parameters like roughness, terrain relief, or dielectric properties. So one is the frequency is very important once we are going for microwave imaging, in which frequency or wavelength we are acquiring the data, or the data is getting acquired. Frequency is nothing frequency, it is inverse of wavelength, and wavelength is speed of light upon frequency, and whereas wavelength has a inverse relation with frequency. Higher the frequency, shorter the wavelength, and lower the frequency, longer the wavelength. So like in visible, we have green, red, and NIR bands. Here the bands are termed as, C band, X band, S band, L band, P band. So depending, the longer the wavelength, the more penetration it will allow. Like X band has shorter wavelength, 2.5 to 3.5 roughly. So it has it gets reflected from the top of the canopy, whereas C band has 3.5 to 7.5. It has a little more penetration. L band is more longer, 15 to 30 centimeters, so it can penetrate more the canopy and reach the ground. So that's why so longer the wavelength, there will be more penetration. So this is so we have to see what kind of frequency the data is being acquired depending upon our application. polarization is another, it is the electrical properties, how our fields are oriented. So electrical fields are oriented. So we have different kind of polarization: HH polarization, VV polarization, HV, VH, or we have a all four polarization available, that is called quad pole data. So polarization is nothing but how the radar antenna transmits the pulse and how it receives back. So like in HH, the it transmits horizontally and receives horizontally. In vertical, it goes vertically and it is received back vertically. So these polarization, impact how the backscattering will happen on the with the object, and it has a characteristics signature, how these polarizations are in terms of the how the object will appear. Like if you are seeing two images on the bottom on the left side, these both are of water only. It is along the coast. But in HH polarization, the water is more clearer, where in VV the water is not so much clear, because VV is more sensitive to roughness, and therefore you are appearing it is appearing little brighter as compared to HH. And HH is the best polarization that is more suited for the flood hazard mapping. But even if there is HH is not available, co-polarized data like HH and VV are more preferred. Other is the incidence angle, how the incident beam, and the angle with the perpendicular with the surface, this is called the incidence angle. So if we have the steep incidence angle or the shallow incidence angle, that also has a role on how the water will be appearing or how the interpretation will happen. So generally for flood mapping, we prefer shallow incidence angle, that is around 45 degrees. You have a better or more than 40, you have a better distinction between the water and the land compared to the steep incidence angle. Other is the dielectric constant, that is the amount of water that soil contains. That also influences the backscatter characteristics of the land, whether your soil is is saturated or dry. If it is dry, you have a low backscatter, and if it is a saturated one, you have a high backscatter. Then the roughness, how the terrain, whether it is smooth. If it is very smooth, like water, you will have a specular reflection. That means entire energy from the radar will hit the water and go away from the water, and nothing will go back to the sensor. That's why the flood water in the microwave data appears darker in color. And if you have a rough surface, it will have a diffuse reflection. And if you have a situation where you have water along, or you have this tree, stem or trunk, you may have a multiple scattering or double bounce effect will be seen. Now, like for the optical data, we have different techniques like NDWI, MNDWI, all those techniques are there to map the water. Here also for SAR data, there are different techniques like backscatter intensity, polarimetric parameters, interferometric coherence, or people have used backscatter intensity and interferometric coherence, or backscatter intensity and polarimetric parameters. But this backscatter intensity analysis is more, is in use. So so what is that is through thresholding, those flood waters are classified in case of the microwave data. So you analyze the backscatter intensity of your data and see those values, how for water it is coming, and the land it is coming by taking by taking cross sections or studying the profile of waters, and then you apply that threshold and say like it is done to segregate the water and the non-water areas. And this is a flow chart which shows the entire methodology how the flood mapping is done. If you have the SAR, like if you have optical data sets, you can have the supervised or the unsupervised classification, or any, you can have the different techniques like NDWI to classify your water. If you have the microwave data, you can have the extraction of sigma naught images, speckle removal, apply some elevation mask, thresholding process, and extract the water layer, then integrate this water layer with the pre-flood mask. This pre-flood mask comes from like from the whatever before the flood you have the water bodies or the lakes or the reservoirs, so that they are taken out from the flood layer. Then you have defining of the flood layer, and then generation of the single bit flood layer, then integration of this with all the inundation layers, and then you can integrate with the administrative boundaries to get the district wise flood statistics, or the number of villages that have been affected, or the transport network that has got impacted, or the flood, how the floods are progressing, receding, flood persistence. So all this analysis can be done once you have the flood hazard. On the right, you are seeing this is a particular one SAR scene, which has, which using some threshold has been classified. Now we have a mask, we apply a state mask because this is areas of Assam. So we have applied a state mask. So we have got this, whatever is outside has been removed. Then we have the mask within the state about the river and the non-river areas. That means river which cannot be, which already has water, and those areas which are high hills within the state, so that they get excluded from our analysis, and whatever remains is only will be called as flood, and which is permanent water will be removed, so that this mask is applied. Once this mask is applied, you can do some refining by putting it on the DM and do some further refining to remove those isolated pixels and convert your layer into, final, prepare the final flood hazard layer. So this is what it is. Basically, from the total water, you remove the pre river water, and you get the final flood layer. So apart from the from the thresholding technique, there are polarimetric decomposition for flood area characterization. So polarimetric decomposition techniques gives dominant scattering mechanism which occurs within the pixels, and thereby aids the interpretation of different features. By preserving the phase, as earlier I told it, the SAR data has two components. One is amplitude and one is the phase. By preserving the phase information, the fully polarimetric data allows the decomposition of the SAR signal into different scattering mechanisms, single bounce or volume scattering or double bounce. These different kind of scattering allows you to distinguish the object on the ground. And for the extraction of the polarimetric parameters, various polarimetric decomposition methods are there. Like you have, you have the model based or the eigenvalue based methods are there. We will not go much into those methods. And this is one of the example where this polarimetric parameters have been used, like normalized Shannon entropy and L1 to distinguish between the water and the non-water, and it has given a clear distinction between the these two out of all other indices. This has given a better distinction between the land and the non-land, and you can classify your flood areas with this technique also. Then you have the SAR interferometry and coherence for flood monitoring. You can also the flood mapping can be done by assessing the changes in the coherence. Wherever there are changes, wherever there is flooding, like this is a pre-flood image. There is no flood over here. These are permanent water. Once the flooding happens, there is a change in the coherence, and you are seeing this green is all flood areas. And once the flood recedes, again the coherence is similar to what it was in the pre-event. So here you require two images. So interferometric coherence is also one of the techniques which is used. So till now, what we studied was the active microwave remote sensing, but we also have passive microwave flood techniques and global flood detection system. GFDS is one such system which uses passive microwave. But these are at coarser level, so they detect the changes in the temperature. Because once the area is dry, you have a different temperature, and once there are floods, the wet pixel will have a different brightness temperature. So once this, so they have a reference pixel. They know once the area is dry, what could be the values, and once it is wet, so how there is a drop in the temperature. So ratio is taken between the wet and the dry pixel to find out the riverine flooding, to give such alerts by the system. Now, coming after having seen those techniques and some basics, there are different mapping services which are provided for flood hazard at global level by Dartmouth Flood Observatory, which maps global flood using MODIS 2 data, and of late they also have started using Sentinel data. So if you go to their website, they map all major floods, and they are also downloadable in a grid, in a grid manner. You can select those areas of your interest. Then you have flood recent services starting from the US Flood Inundation Mapping Repository, USFIMR, which, and also at Indian level, we have through our NRSC, which has a under its disaster management support program, it provides near real-time flood inundation maps using different kind of satellite data sets from the Indian remote sensing as well as from the foreign satellites, and the data sets are kept in the Bhuvan portal where they can be accessed. Now coming to some of the applications, once you have that flood hazard layer with you, either through the optical data or through the microwave data, you need to have some kind of application. So this is one of the examples that was carried. That is, that is about the flood hazard zonation, and we know flood hazard zonation is one of the more important non-structural measure that helps to mitigate the floods. So under ISRO DMS program, NRSC has generated flood hazard maps for different parts of the states like UP, Odisha, Bihar, or West Bengal, Assam. Some of them are available in the Bhuvan portal as digital layers also, and in the form of atlases also. So one example is for Bihar, where we have data for last 2 decades from 1998 till 2020-21. The data is available. So for using last, this flood hazard, so all these layers, annual flood layers, are extracted using around more than 100 years of, more than 113 satellite data sets for last 13 years, and they have been integrated. And considering the gauge data also from the rivers which are present in the Bihar, and also the flood waves, number of flood waves, it gets affected in each year. So these layers have been integrated with the waves and the gauge data to assess the flood hazard index. And we have, if you go to the Bhuvan site, you have this flood hazard zonation map, which shows which areas are highly vulnerable to the flooding. That means most of the times they were flooded out of the period that was considered. Then which are under moderate flooding, high flooding, and low flooding. So these maps have been approved by the NDMA and the Central Water Commission and IMD, and they also verified by the Bihar State Disaster Management Agency, and they are available in the Bhuvan portal. If you go, you can see these maps and zoom. It is in a GIS enabled version where you can click on the particular pixels to get the information, whether it is under very high hazard, low hazard, the name of the village. And you can also compute the area statistics if required. You can have your own customized polygons to see how much area is under which category in these areas. Once you have, there are other techniques also from the geospatial point of view. One is that from satellite images you extract the flood hazard. Other is either if you have DM, if you have satellite images, you can extract slope, aspect, all those information can be extracted from the DM. And from the satellite images, you can have the land use, land cover map. You can have elevation data from the DM. You can have the river density. You can have all those morphometric parameters, and using hydrodynamic modeling tools like HEC-GeoRAS, or you can have the discharge data and give that as an input to the model. And from the satellite images, you can draw stream river profile, stream centerline, flow path centerline, cross sections, and having the discharge data from the field, we can compute the extent of inundation for a particular return period, and also create the flood depth map. And also from the other source, by using DM, also we can have a multi-criteria analysis to which areas will be more impacted by floods, as well as from the hydrodynamic modeling perspective. And can we can have a flood hazard potential mapping maps. This is one of the examples there where we have done the flood hazard simulation for the Sabri River, which is in in Andhra Pradesh, one of the tributaries of the Godavari River. So we had the ALTM, DTM. We have used HEC GeoRAS for extraction of river geometries from the satellite. Land use land cover has been extracted. Then extraction of Manning's coefficient from the satellite data. Delineation of flood inundation, then hydrological model was set up, and then water surface profiles and the flood inundation simulation has been done, which has been validated using the satellite images. So this is from the simulation results. This is from the satellite on the same day. The pass is also the same day. 23rd we have simulated, and 23rd there is a satellite pass. So we have validated our results, and then this kind of simulation can be generated. And once your simulations are perfect or are well in accordance, you can we also have attempted to create one flood inundation library. That means you have different scenarios for different water levels, right from the initial stages of flooding to the maximum flooding that can happen over there. So you can have those kind of scenarios, so that we have a flood inundation library. That means even if we don't have satellite data on that particular day, we can use the water level information to assess what could be the extent of inundation, because we have gauge sites on this site. We have 3 gauge sites. So for that, every day Center Water Commission gives the water level, and if we know the water level, we can identify what could be the extent of the inundation. So this is what how it has been done. Observed flood extent from the satellite data, and from the through simulation, how much the match has been. We have used the ALTM, DTM over here. Once you have this kind of information, you can simulate if the water level increases, what could be the submergence in the adjoining areas, and how much infrastructure will get impacted or affected, which roads will be submerged. And if you if you have a building footprints, you can have a 3D building also over here to see what height of building will get impacted. And this model can be will help to identify such kind of damages. This is one example where flood persistence. Once flooding initiates, it happens for or almost weeks and months. So since we have continuous observation from satellite data, they have a pass after 3 days, 5 days, or 10 days, whatever interval the temporal resolution is there. So we can continuously map these areas and see where the water is persisting for a larger duration. Those areas where water is persisting for a larger number of days, you will have the problem of epidemics. You may have the problem of people not getting good quality of drinking water. You may have problem of agricultural crops wilting. So such information is very crucial for the planners to mitigate, and also to see which areas they need to mobilize their resources, because this is one of the district, but flooding is only concentrated in these pockets and not in the entire district. So if we have these maps, we can have a focused mobilization of our limited resources during the times of flood. Now, once you have flood, we also require depth and geospatial information technology, because of its the availability of DEM, digital elevation model, from you must all be hearing about the SRTM, DM, shuttle radar topographic mission, and then there are different kind of DMs. So these DMs allow you to have the estimation of the flood depth. So if you have the flood from the satellite data, we can associate the flood polygon boundary with the DM to get the depth, and then we can subtract the normal depth from the depth of the flooding to get the flood depth and have our flood depth assessment, because only the extent cannot help you. Once here we have the extent and the duration, we know these areas are flooded, and we also know the duration, the number of days. But whether the depth is also critical, if depth is less, even if it is flooded for 10 days but depth is very less, it has not so much potential of being impacted as compared to the areas which is higher depth. So depth also is an important information once you are trying to develop any flood mitigation strategy. So now coming to the flood damage assessment, once flood happens, we also need to assess how much roads have been impacted, which villages got impacted, what is the land use or the croplands have got submerged. So once you have flood hazard layer, if these can be integrated with land use, villages, administrative boundaries to find out the land use affected or maroon villages, all those information can be extracted using the GIS softwares available. This is example from one of the high resolution satellite images that displayed as data at at 0.65. This is from the world view. This is at 0.65 meter. We are able to see each houses. All the building footprints are very clear, and also the tree cover, the roads. All the structures are very clear. So this kind of data, very high resolution data, helps you to identify those kind of building footprints, and identifying the kind of settlement is residing, whether it is a slum area or whether it is a government building, whether it is some kind of school, playground. So this kind of will help you to identify those areas. Then now once we have the flood hazard layer, we also require the risk. Now, what is the risk in the? We need to map the flood risk. For mapping the flood risk, again we require hazard, exposure, and vulnerability. Hazard anyway we can get directly from the satellite images, or through by the modeling techniques, where we can get the extent of the flood inundation that will happen on due to at different discharges. Then we need to have the exposure. Either exposure is the population residing in that area, or if we are assessing the crop damages, then the exposure is towards the crop, whichever crop is exposed in that area. And the vulnerability factors, which is a number of factors decide the vulnerability, whether those if it is in case of population, how old is the population, whether the population is literate, or whether the population is economically sound, whether the population is more of the young people or old people, disabled people, or the condition of the building or the financial condition. If it comes to crop, then what kind of crop it is there, what is the stage of the crop, how long the crop is inundated. So all those factors will decide on that. And once we have all these information, we can integrate them and compute the risk. This is one example trying to show you the risk for the paddy crop. There are standard curves, standard information which shows that if the days of submergence is 1 or 2 days, 3 to 4 days, 5 to 6 days, 7 days, and if we know the stage of the crop, it is at vegetative stage or ripening stage, maturity stage. If we know the stage, we can find out what could be the estimated yield losses. So that means days of submergence can be computed from the satellite data, and stage all we can have from the ground, which month the flooding has happened, and also we know what will be the height of the crop. And we also have so such kind of here you can see the exposure is to the paddy crop. This also can be derived from the satellite images, the area that is under paddy cover. Hazard means which area will be of our flood impacted, can be drawn from the satellite data or through modeling techniques. And then we have the vulnerability. These curves are available depending upon the flood depth and the maturity stage. So there are damage curve for rice crops where the flood duration is 1 or 2 days, 5 to 6 days. So we can compute the agriculture economic losses. This is one of the recent example of floods that happened in Bihar in last year in 2021. And no, we have done one study to find out the crop lodging, identify the crops that have been lodged due to heavy rains. These are standing crops on 18th and 19th. Due to flooding, these crops got laid down. Their vertical nature has changed, and this is through the polarimetric study. We have tried to identify whether these we can detect them through satellite studies. So we were able to detect, get good results from using different anisotropy, alpha angle, and entropy, and we were getting that because of the change in the nature of the crop, the angle while it is standing and while it is laid down, these angles are, alpha angle has helped us to detect the changes. Now, coming to one more example of the Chamoli flash floods that has happened in 2021, and it was widely known, and people have assessed this disaster globally, and it was more in news because it is a unique disaster that happened in the period of February. So just I'll show you some examples, some slides where we have worked on this particular disaster. There was a rock slide around 5,400-meter altitude in Ronti Glacier, near Ronti Glacier. There was a detachment of the block, and that block got dislodged and then rolling down along with the ice and the rock material, and it traveled around 1.7 kilometer. There was a drop, and there was a huge flash kind of floods downstream, which led to damage of two major hydropower projects along the route, and also damages to the bridges, and also some of the nearby road connectivity was there. So we had used, satellite data was used in the entire study to identify what could be the volume of the material that has got dislodged from this place, what could be the volume of water, or what could be the height of the water that would flow down the stream, and how much elevation of water will rise. So this kind of analysis we had done, and we had these are satellite images before the rock slide, and after the one day after, and few days after, we have captured through a different satellite from the Indian satellite, and also as well as from the planet data. So this is one of the data from the Pleiades, which shows you the closer view of that place from where the mass got dislodged, and this data was obtained under international charter. Charter is a mechanism where the satellite data in times of crisis is given by all the space faring nations to support such major disasters. So this data was obtained under that, and you can see we are able to compute the volume of the material and the depth and the change in the profile of the area. Like over here, you can see there is a drop in the elevation because of the mass got dislodged from this area. So we had Pleiades stereo data sets were processed for satellite triangulation using a rational polynomial coefficient RPC technique in photogrammetric environment to generate a DM. We generated a DM based on the data sets we got, and from the post-event data analysis, we were able to see that in an average, thickness of the detached and the dislodged mass was estimated to be 70 meter, and also from this we were able to give the 23 million cubic meters of volume of material got dislodged. So that's why these DMs are very important, to find out the volume of the material that will gets dislodged. And this is one of the field pictures because we went to this area through the support of the state disaster management and the Air Force we were visiting, and this is what we were seeing in this picture, through the satellite, and this is from the field. How it looks, little angles are different, but this is the same place from where that area got dislodged. And see, these satellites help us to see what was there in, this is the Chamoli area only, this is the bridge, and this is the area where this Tapovan, hydropower project was there, and this is downstream of that. So due to sliding, a lot of energy was generated, and it damaged all these bridges. And you can see this is the post disaster, the situation. This bridge got damaged. There was one hydropower station over there. It also got washed away. This is the downstream main hydropower where major damage has happened. So this also got washed away. And downstream of this hydropower, there were some settlements over here. They also got damaged, and the river got widened. And these are the pictures of those points that were collected by the people on the ground on that day. And recently we visited the same area in March. Also we visited this area, and this is the same site which you are seeing in the satellite data. It looks on the ground, it looks like this. So this is the new bridge that has come up. This is the place where the bridge got damaged, and now they have put a mechanism, a device for the alerting the people to read the water level. Sensor has been put to alert the people if the water level rises. You can see this is the amount of height the water has taken once it came down the Rishi Ganga river and then to the Holy Ganga river, around 70 to 80 meter, and somewhere more than 100 meter also high the water has been, and it has eroded the entire. There has been a lot of toe erosion along the river. This is the hydrodynamic simulation that was carried at our place to identify what could be the depth of water and what could be the the extent of flooding. So this information was also carried out using the initial information that we were getting through the using the different mic model we used, and we gave out what could be the velocity of the moving water and the depth of the water. Then from the satellite images, we were able to also identify those areas where there was impoundment. In certain areas, these areas are not approachable, because at that point of time, these areas are very high altitude, and it is not simply so easy to approach to these areas. If you see this area, here, this is the place where that bridge downstream here, somewhere down we have that bridge, and upstream you have the glacier. And if you go around this, it is somewhere here that river flow got blocked, whichever I am showing over here. This is the field picture that was taken from the from the helicopter, and same area, it is a steep gorge. It is difficult for the satellites also, but we had to do some processing to enhance this area and to get the estimate of how much volume of water is in this area which got impounded, and what is the dimension of the lake that is developing on the upstream side. So it was because of the satellite images only we were able to identify those places and give information on those places. So this is how the area looks before the disaster, before and after the disaster. There was a lot of snow fall in that area prior to the event, and then this is the time once the event was happening. These satellites were able to capture. They were orbiting on over that area, and this is as the event was happening, these satellites were moving and were able to capture. So there was a lot of snowfall prior to the event, and then this a lot of snow was under the dust, or it got melted. So we, from the historical satellite images, we were able to see that this area also had experienced similar kind of, but not of such magnitude, floods or the dislodging of the material, in that area earlier also has been noticed. And there was, we had done some study to find out how was the development of that, where from the crack developed and the material got dislodged by using historical or the temporal images to find out what has happened and when it started. There was a paper also brought out by us. This you can go and download this paper. It is in Journal of Indian Society of Remote Sensing, and it has been widely referred. There are almost more than 40 references for our article now, and also it has been downloaded. There are more than 4,000 people who have, I think, downloaded or read this article. It is freely available. So once this, so if from satellite such kind of data is available, it can be used for mitigation, because whatever from satellite is coming, it is in the form of maps. Now how that those maps can be actually used on the ground is the main potential of satellite technology. This is one of the flood hazard maps that we generated for Assam, and Assam State Disaster Management Agency has used that map in form of actions. They have, how they have used is that whatever information we gave, they converted into information, those maps into action oriented information. Like those villages which are high underwater, there should be mobile medical teams, there should be water tolerant crops should be grown over there, there should be contingency plan, there should be the water, water and water availability should be made during the times of flooding, and houses should be made at a higher level, flood shelter should be identified. So this kind of, this Morigaon, this is one example of Morigaon district, and the administration has used our maps, and they have made some guidelines and provided to the state, so that in times of crisis, whichever villages we have identified under high risk, so for all their concerned departments are asked to take actions, and in terms of relief and rescue, so that the mitigation or the kind of things can be quicker. So now other one more technique is there. We, from whenever we speak about floods, we generally speak about the gauge data also, from which we can get the water level, because water level is very important in the entire flood management, either the discharge or the water level data. Since these gauge sites that we have from the Center Water Commission, they are limited and they are sparse, and during flood times they may get damaged also. So satellite altimetry is one of the fields that has come up, which helps us to get to have virtual stations, and we can also assess the water level, and they can be used for studying the river discharge, reservoir volume, for the calibrating and validation of our hydrological and hydronic models, develop rating curves, and generate near real time flood forecasting, reservoir operation. So such kind of operations are now possible with the satellite altimetry. So Altai and India also has a role where we have developed altimetry mission is launched with the help of France, that is Canes Space Agency, and that is called Sarar Altica. So what it does, it sends the pulse radar, it emits radar pulses and receives the echoes reflected from the water surface, and then it can measure with an accuracy of few centimeters the water height, and we can derive the water level from the duration between sending the pulse to whatever duration it takes for the sending the pulse, and same pulse getting back. So this is the typical altimetry satellites. So it can, R by range, C is the velocity of light, T is the time by 2. So it can, that way we can find out the water depth is gauge height. It helps us to have the water level information. Other example, major example, as I've told you, if you have a DM, from DM, we can have number of applications. We can have flow direction, we can have flow accumulation, stream order, we can have the flow length, watershed delineation. So number of application can be developed if the DM is there. Using we also for the watershed prioritization, if we have DM, we can find out the morphometric parameters. If we have precipitations, now these days satellites allow you to have precipitation data, soil map, and we can have the vegetation and agriculture practices. You can do the SCS curve runoff or the Rusley method. There are different kind of soil erosion risk assessment or different kind of methods to prioritize our watersheds. So in that, remote sensing has a very important role. Remote sensing also, because of the DMs, helps you to assess the volume of the material, how much if there is sudden landslide and the water gets obstructed. So what is the volume of the landslide material? What is the upstream water profile? You can have a 3D visualization of the landslides. For flood forecasting, it is an important technique, and remote sensing helps to a larger extent these days, because land cover is required. Whatever hydrological model we have, Once we set up the model, we require land cover, soil map, rainfall, elevation. All these have a role, then we can have the rainfall runoff modeling, hydronic flow routing, calibration, validation of the model field with the discharge data. This all can be done. So this is one of the example that has been done for from the IRS for your Kedarnath, the extent of the spreading that happened or could happen under different kind of scenarios. We are using, they have this kind of output also WRF based rainfall outputs also simulation what could be the rainfall at certain intervals, and then also we have automatic weather stations installed at different places. No, precipitation is an important input for whatever kind of modeling we are doing or analysis we are doing. So these days from the satellite, there are a number of satellites which allow you to assess the rainfall either from the latest is the GPM IMERG data, at 10-kilometer resolution. You can get from there. Soil moisture is also important, is a key variable in examining the global water energy cycle. So from the satellites, that also can be obtained. There are many satellites which give you as a product directly as a soil moisture product like SMAP, AMSR2, which give you this data. Then we can have the snow cover dynamics mapping, because the changes in the snow cover will guide you which heavy snowfall in Himalayas leads to higher snow cover area in spring season and increases the probability of flash floods, landslides, sudden increase in river flow and associated hazards in the region. So therefore you need to also map this snow cover, and these satellites help you to map this snow cover. Then urban flood modeling is one of the other key area where this geospatial technology is being used, to build the base information and then to route the flow, to construct this kind of drainage stormwater management model and see which nodes will get flooded at what interval of time and what will be the volume of water, at those nodes. Then coming with this, with these applications, we'll just come up to the recent trends, what is happening in today. Now, in terms of flood hazard, the open data access is being provided because flood hazard is such a phenomena that impacts a lot of human population. So the stress is on making these data sets available openly. So you are finding most of the missions that are coming up, like the Sentinel-1 and Sentinel-2, which are in operation, are freely available, and also the upcoming mission that is being launched by NASA and ISRO, the NISR L-band, the data will also be made freely available. Then use of drone for mapping and relief monitoring, because these drones can be employed any time when the disaster happens, unlike the satellites. Then cloud computing is another field where it is gaining importance, because a lot of data has to be used in such analysis, and the volume of data is very high. So there are a number of platforms like the Google Earth Engine platform, where everything can be done on the cloud and nothing has to be done at your machine end, and you only need to download the output. Then a lot of people are using social media like Twitter, Facebook, whatever inputs are coming there to assess indirectly the hotspot analysis or what kind of flooding is happening. Then artificial intelligence, machine learning applications are also becoming very popular to identify the areas which will get flooded, or how the flood will be in times to come. Like our India also, this Center Water Commission and the Google have come together to use this technique to give flood alerts to the common people. A number of web portals are now in practice, which are providing free of cost these data sets. They are hosting the data for the flood forecasting or the weather research forecast outputs. Like in India, we have the MOSDEC from the Space Application Center, Bhuvan from NRSC, which hosts all the flood hazard mapping products. Then we have the Vedas from the SAC, which gives you analytical. They have, you can do the NDVI analysis, or you can do the your own time series analysis. Such kind of portals are coming. Also at global level, you have GDEX, which gives you flood disaster. Then analysis ready products. Now that the trend is that the user should not download the data and analyze the data. Instead of it, the product should be ready so that he can readily use it for his purpose, instead of doing all the pre-processing. And that is where now global, if you see one example is Global Surface Water Explorer, GSW, is such a portal which allows, which gives you all water rated outputs for last from 1984 to up to 2021. What is the maximum extent of water? How the water has changed? Now that all kind of statistics, month wise, year wise, all that it can be done on that, and also can the data set can be downloaded and directly can be used for your mitigation purposes. So with this, I'll stop, my presentation by giving the last, what is the trend happening, and I thank you all for listening patiently to this